it, get it, get it, get it, yeah, hey, get it, yo, ecstatic, fantastic, get it, wow, get it, bad news and good dope, powder, potion, pill, smoke, baby, how you trying to go? Duro or dulce, fast or slow, yay, no, it's okay, you can have it your way, nah, it ain't all good, but baby, I'm cool, feeling great, feeling good, how are you? 10% condition, 90% response, survival mathematics, the number man song. Old dad dropped the jewels so pure, when the times get raw, it's something I recall. Sometime I don't remember it at all, and I get stormed by the weather, but no umbrella. Sky release pressure and the ground get wetter. My outfit effed up, I could've looked fresher, but guess what? The hell with parade day rain, tsunami of sunshine, the mama just the same. Life is a game, I heard the homie say, but I came to win. Dante, get it, play, get it, Brooklyn, get it, ecstatic, a day, speedball, bad news and good dope, powder, potion, pill, smoke, baby, how you trying to go? Duro or dulce, fast or slow, yay, no, it's okay, you can have it your way, nah, now's the time, but baby, I'm cool, feeling great, feeling good, feeling good, feeling good, feeling good, feeling good, feeling good. Every day, every day, having a good time, every day, having a good time, every day. Having a good time every day. That's cool.
All right, so last week we started talking about trees, and we gave a motivation for looking at trees because they provide a potential for efficient operations for all 4 operations. Create, retrieve, update, and destroy, putting stuff in, retrieving stuff, deleting stuff, all that stuff that we want out of our data structure. We also gave a very brief glimpse of what a tree looks like. But more formally, a graph is a collection of nodes, or sometimes called vertices, and edges connecting individual nodes. So pairs of nodes, pairs of vertices. Graph theoreticians will call it vertex or vertices for plural. We'll call them nodes because ultimately our vertices are going to be holding data, and nodes are a way of holding data at each point in the graph. A tree is a connected acyclic graph, that is a graph with no cycles. We also looked at some other definitions here. A path in a graph is a sequence of connected vertices. A simple cycle is a path that ends up back where it started. And then the length of either one of those is the number of edges on it. So let's take a look at an example here. This is just a general graph. This is not a tree yet. Why? Because it has cycles. Let's go ahead and note some things here, first of all. What are the number of nodes? This is usually denoted as a vertex set and the size of a vertex set. And we use the variable n there to denote that. I count 1, 2, 3, 4, 5, 6, 7 nodes here, right? So there are 7 nodes, and the number of edges, an edge connects 2 vertices. That edge connects those 2 vertices. Now don't think about anything about this crossover point there. That doesn't mean that the edges are connected, right? This is one edge, this is another edge. It's just that we can't always draw them so that there are no intersections of those edges. A and B do not have an edge, and so we do not have an arc between them, right? So how many edges do you see here? I see 1, 2, 3 out of there. So let's go ahead and highlight them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right? I see Did I get it right? I think I got it right. If I didn't, sorry. Right? Maybe there's 13, I'm not sure. But in any case, there are 12 edges here, right? There are also paths, right? A to D is a path, right? What is the length of this path? Well, it's just an edge. So going from A to D here, its length is the number of edges along it. So it is an edge is a path of length 1. I can also go from A to D to B to E, right? And that'll be A to D to B to E. That's another path right there, right? And that is of length 3, right? Now here's another path. A to D to B to E to back to B, back to B, back and forth, and finally you go over to G there. That is a non-simple path. We're not going to consider paths like that. What we want to do is we want to store data in this graph, and we want everything to be efficient. It's not going to be efficient if you keep going back and forth for no apparent reason whatsoever, right? So we're only going to look at simple paths, paths that traverse any edge more than at most once, okay? What about A to B to E to C? That is not a path because there is no edge going from A to B. So it's not a path. You could say that the length here is infinite of that path if you want to. By convention, sometimes we do that. Okay? All right. Well, is this a tree? No, because there are cycles in it, and a tree has no cycles. What do I mean by a cycle? Well, here's a path going from A to E to G, over to C, back over to D, and back over to A. I ended up where I started right here. That cycle has a length 1, 2, 3, 4, 5, right? So I could go, again, from A to E to G to C to D back to A. Now, the length of that is going to be the number of edges on it. 1, 2, 3, 4, 5, but I've already gone back over here to A. So here is of length 5, okay? That is a cycle. Right? There are lots of cycles here. We're not going to enumerate all the cycles, because what I want is ultimately I want a connected acyclic graph, a graph with no cycles in it. So let me go ahead and switch my color over here, and let's start getting rid of some of these edges. Right? Let's go ahead and get rid of that edge right there. Right? Now, does that take away all of the cycles? No, there's still at least one cycle right there. Right? So let's go ahead and take away one of those edges right there. Okay, there we go. We still have some cycles. Right? Give me an edge that I could take away. How about B to E? There we go. Still some cycles, right? So I took away 3. I'm not sure how many more I need to take away here, but go ahead and identify another cycle here. How about C, B, D, and F? What if I were to take one of those away? That breaks that cycle. Okay. Are we done yet? No, give me another edge that I should take away. Say what? A and E? Okay. Because there was a cycle between A, E, and F. All right? Before I ask you another one, what if I were to do this? What if I were to take away that edge right there? That's too much. That isolates this B over here, right? And it creates 2 connected components. This stuff over here is connected, B is connected with itself. It might have another vertex over here, I, or something like that, but it's disconnected the graph. And that's not, you can consider that in graph operations, but we're going to, and that's called a forest. That's not called a tree. Why is it called a forest? Because it's still it's a collection of trees. Right? So I'm going to go ahead and restore that one. Now you give me another one. Give me another one that will break another cycle. In fact, give me the cycle. Is AF involved in any cycle now? Nope, because I can never get it back around to A from another direction. I could always go back to A on the same edge, but again, we're considering simple paths and simple cycles. Right? So I see one right here. 1, 2, 3, 4. Right? There's a path of length, or there's a cycle of length 4. Let's just go ahead and get rid of that one right there. Okay? Do we still have a cycle? Right, which C to G to D to F back to C. So let's go ahead and break that cycle right there. Okay. Is that good? Yeah, I think so too, right? Let's make an observation. I went from 12 edges down to what? How many edges are left? 1, 2, 3, 4, 5, and 6. Right? 6. It's still connected, right? From any vertex, I can get to any other vertex, right? I can go from there to there to there to get to G. G, I can go to B. From F, I can go to C. From G, I can go to C, right? So I'm convinced that this is now a tree. In fact, tell me about that number right there. Right? What if I were to delete one more edge? Right? Then I would have necessarily a disconnected graph. Try it. From any of these, you're going to end up with two components there. Okay. What if I were to add any one edge? What if I were to add A to B? We didn't have that before, right? Adding that edge induces a what? 1, 2, 3, 4, 5. There's a cycle. So let me undo that. Right? What is it about this number right here that tells me that this is a tree? Right? That's my first observation. My first observation that is that in a tree, with n vertices, nodes, there are exactly n minus 1 edges. Right? Why? Because any additional edge will induce, in other words, create a cycle. Right? The removal of any edge will disconnect the tree and give you what we called a forest. Right? So that's my first observation, right? Now remember, why are we looking at trees to begin with? Because we want data structures. And for there to be data structures, there needs to be structure. Why do we like structure? Because we can exploit that structure. Right? This seems like a really, really cool structure to have, because you have the exact same number of edges, minus one, as you do vertices. Okay? That tells you that the graph is very sparse. There are a lot of graph algorithms out there that are very, very difficult to solve on general graphs. Because general graphs can be dense. There can be any structure, any topology whatsoever. But a lot of those algorithms suddenly become magically easy. Again, not magically easy, but they suddenly become easy if you're dealing with trees. Why? Because they're sparse. They only have n minus 1 edges. Generally, what you could have is order n squared edges, because for all pairs, you can have an edge. In fact, if you're in a complete graph, it'll have n times n minus 1 over 2 edges. We're not going to look at that, though. We're not going to get deep into graph theory here. Okay? My second observation is, how can I get from one point to another? I'm going to call this a source vertex, and I'm going to call this a destination vertex. All right? From a source vertex to a destination vertex, there's going to be some path, P1. Okay? Why? Because it's connected. Right? Remember, if it's disconnected and there is no path going from B to D, then I don't have a tree. I have a forest. Now tell me, could there be another path going from D to S, P2 there? Right? Could there be another partial path that maybe shares this path up to a certain point and then diverges and then goes off over here? Can you have that in a tree? What's this thing right here? A cycle. What's this thing right here? A cycle. So my second observation is that in a tree, between any two nodes, there is exactly one path between them. Right? Very, very highly regular properties here. Right? So from getting from one place to another place, there's only one way to do it, because there's only one path. If there were two ways of doing it, then you would have a cycle somehow. Okay? All right, so like I said, we like structure. What we're going to do is we're going to add more structure called orientation. Orientation, right? Trees can be oriented. Right? Top to bottom, left to right. Right? So for example, let me come back over here. right? And it's not going to be the same tree that we looked at before, or it's going to be the same graph we looked at before, but it's going to be a different tree here. Let's see, trees, and there's the same graph, but with a bunch of vertices removed. Let's go ahead and get rid of this stuff now. Right? With a bunch of vertices removed in order to make it into a tree. Right? You can verify that. They're the same, let's see, 7 vertices. There are some 6, right, 7 minus 1 edges there. 1, 2, 3, 4, 5, 6. That makes it a tree. Okay? All right. So, what I want you to do is imagine that you can magically grab this tree by any node, pull it out of the screen, and then dangle it in front of you and let gravity take over, right? There are a couple of ways that you could do that, depending on how you wanted to grab it, right? For example, if I grabbed it with A, right, and I dangled it and let gravity take over, then I would orient it top to bottom. And what would be hanging off of it would be D, E, and F. D, E, and F. Right, there we go. Now, here's another question. Why did I immediately say that D came first and then E and then F? The way that it's written over here, I've got F, D, and E. Why did I reorient it so that I have D, E, F here? Because that's the order, right? I'm going in natural order here. I'm going in alphabetic order, right? In other words, we're going to orient this stuff from top to bottom, but also we're going to orient it left to right. So that there's a concept of left child, middle child, right child here. In fact, we're going to use that terminology. We're going to call these things parents and children and grandparents and ancestors and descendants. Why? Because this is how you draw a family tree. Okay? All right. Well, hanging off of D there, I don't have anything else. Hanging off of E, I don't have anything else. But hanging off of F, I've got C. Hanging off of C, I've got G. And hanging off of G, I've got B there. That's one way that you could do that. All right? So what I'm going to do is I'm going to go ahead and minimize, resize this. Where is it? Resize. There we go. And put this off over here. What's another option? Right? Go ahead and give me your favorite vertex up there. I just did it with A because that was natural. Like, what's the first one? Go ahead and grab it from another vertex, pull it out, and then dangle it, and you'll get a different topology, a different shaped tree. So go ahead and yell out your favorite vertex there. F? Okay. Going with the last one, right? Oh, I guess no, G would be. E, F, G. Yes, G would be last. Right? There's F. Hanging off of F, I've got A and C. Hanging off of A, I've got D and E. Off of C, I've got G. And off of G, I've got B. Right? There's another way of looking at it. Again, it's organized top to bottom, left to right. Okay? And we use the following nomenclature. Let me go ahead and grab the figure instead of having to write it all out. Oops, there we go. Trees. And, oh, I don't have, oh, no, there it is. Nope, sorry, that's different. Okay. All right, so let's go ahead and just draw it out. Right. If this is a node U, right, then U, the one coming off of it, is the parent, P. Right? This is the parent node, parent of U. Right? You can also have children. Right? In fact, what I'm going to do is I'm going to almost immediately, I'll just label these. Right? These are going to be children. So if I have C1, C2, and C3, for lack of a better term, right? Then these are going to be the children. Up here, these are ancestors. Down here, these are descendants. And so we're orienting it like a family tree. You can call these siblings, right? These would be siblings. You can use other terms like cousins, aunts, uncles, right? Grandchildren, grandparents, and stuff like that. That's the orientation, top to bottom, left to right. Okay? That's still not enough orientation, right? At the very top, we have a single node called the root, right? Any node with 0 children is called a leaf. Right? So let's look at another example here that I've already that I'm not going to write out. I'm just going to go ahead and bring it in. Come on. Let's go with this one right. Yeah, this one right here is good enough. All right, there we go. So if I were to look at any individual here, B, it has 2 children, a left child and a right child. Its parent is A. Its left child is D. Its right child is E. Right? We also have the root here. This is a root. Now, what did I just define as a leaf? Well, a leaf is anything with no children. That would be L. R. What about H here? Is that a leaf? Nope, it has a child N there. Okay. So N is a leaf, O, P, Q, and K. Those are all the leaf nodes. These are all leaf nodes. Right. If it's not a root and if it's not a leaf, then it's just, these are called sometimes internal nodes. So let me go ahead and just highlight all of these. There we go. These are all internal nodes. There we go. And then up at the top here, we have a special root node. Now, immediately you can ask yourself, wait a second, trees don't grow like that. You go outside and down at the bottom are the roots, and then it grows up and the leaves are at the top, right? That's not how our trees work because of Cayley, a mathematician that introduced this concept 150 years ago. Instead, our trees grow downward. Why? Because we like to read in English left to right, top to bottom. Right? And as a consequence, since our nodes are going to be holding data, we're going to read them left to right, top to bottom. And that's why our trees grow downward here. Okay? We need a little bit more orientation or a little bit more, again, this introduces a parent-child relationship. But what we want is more structure. Right? Suppose that each node had at most, is limited to at most 2 children. Right? In other words, it can have no child, 1 child, or 2 children. 2 children. Then what we could do is we could orient it left to right, and that there's a left child and a right child. Right? Or both, or neither. Right? Neither? That looks right. That looks better, at least. All right, there we go. So that's going to be called a binary tree. This is called a binary tree. Now, why is it called a binary tree? Binary base 2. We are limiting the number of children to 2. Okay? So over here, I'm going to go ahead and erase all this stuff and restore the original tree. There we go. And you tell me, is this a binary tree? Yeah. Look at A. It has 2 children. B has 2 children. It doesn't have 3 children. If it had a 3rd child right here, then it would not be a binary tree. You could talk about ternary trees or quaternary trees or whatever. We're going to keep our attention here to binary trees. What about E? It has no left child, but it does have a right child. Right? At most 2 children. You can have 1 child. What about M there? It has a left child, but no right child. So you can have one or the other, or neither, or both. Right? For example, O right here, that is a leaf because it has neither left nor right child. And so consequently, we have what's called a binary tree. Oops. This is a binary tree because it has at most 2 children. Okay? So some more terminology here. Terminology, right? So what we have is the depth of a node, U, is the length of the unique path from the root to U. Right? Okay? So remember, we have a tree, a connected tree. We already observed that between any 2 nodes, the root node or some other node, there is exactly 1 path. Right? There is not a second path because that would induce a cycle. That's why we're comfortable with saying the unique path, because it's guaranteed to be 1 and only 1. Right? So the depth of a node is the length. Right? So let's look at a node, and let's look at its depth. Well, what about, let's go with A, B, C, D, E, F. All right, we won't do them all, but let's just go ahead and do some subsequence here. What about B? If I start at the root node and traverse down to B, how many edges did I have to traverse there? 1. Right? Likewise, C, right? Depth. Right? So these are depth 1 nodes. Okay. What about D, E, and F? 1, 2, 1, 2, 1, 2. The depth of all of those is going to end up being what? 2. So now let me go back to the first one that I skipped. What is the depth of A? What is the depth of the root? Yeah, it's the path to itself. Now we don't look at self loops here. Come on, I don't want that. There we go. We don't look at self loops. That's called a multigraph. I think. No, that's not a multigraph. That's I forget what it's called. But there's a term for it where you can have self loops. But we're not going to consider that. If you're already at A, you can stay at A. I'm already sitting here and I could stay here. How many steps did I take to get here then? 0. Right? So by convention, the depth of the root is going to be 0. Okay. What is the deepest node here? From the picture, I can see that it's going to be R. You tell me, what is the depth of R? Well, to get to R, I would have to go from A to B, to D, to G, to M, to F, R. How many did I traverse? 1, 2, 3, 4, 5. Right? So the depth there is 5. That's also the depth of the tree. Depth of tree is going to be 5. Why? Because that's the deepest node there. Right? It doesn't matter that there's only one of them. If I got rid of this, then I would have a whole bunch of nodes at depth 4. Right? That's still going to be the depth of the tree. So 2 observations or 2 corner cases, corner definitions here. The depth of the root node is 0 by convention. Right? The depth of the tree itself is the maximal depth of any node. If I added another node at the end, or it's hanging off of R there, right? If I were to hang another node, say a right child over here, X, right? Then the depth would end up changing to 6, right? Because I've added something deeper. But what if I didn't do that? What if I added X instead? Oops. Okay, let's go ahead and get rid of it, I guess. All right, there we go. What if I had added X up here instead? Then the depth would have remained the same at 5. Because I didn't increase the depth of the tree. Instead, I just increased like another node at the same depth here. The depth of the tree would still remain at 5. Okay? All right. So how can we exploit this structure? Right? Lots of structure here because we've been adding structure and structure and structure. Right? So suppose you had a full binary tree. Right? That is, every node was present at every level or depth, right? Up until the maximal depth of the tree, right? As an example, is this a full tree? No, because there's an entire tree that would be subtree that should be hanging over here off of C, right? There should be an entire tree hanging off of E. And all the last depth nodes here should all be here as well. And there's no depth node or there's no deeper node than K. Right? So instead, let's look at another example here. In fact, I'm going to start out here with just dots. Okay? What if it was a depth? In fact, let's go ahead and move this down a little bit and give myself some room here. So let's look at the depth here at 0. At depth 0. And let's look at the number of nodes at that depth. Right? So if I just had a single node here, then I would only have one node. Okay? Now, sometimes people like to call this a seed. Why? Because if there's only one node, right, it's the seed and the tree hasn't grown at all yet, right? We haven't grown anything off of our tree yet. Right? All right, let's go ahead and add the next depth. At that depth, I'm going to have both children. 1, 2. And so there are 2 nodes at that depth. At the next node, depth 2, then I'm going to have 1, 2, 3, 4. There are going to be 4 nodes at that depth. Right? Let's continue. Right? At depth 3, how many nodes am I going to have to draw if I drew them all? 2 children for each one, so 8. Right? Dot, 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 dot. What if I asked you about depth, say, K? How many nodes are going to be at that depth? What's the pattern here? 1, 2, 4, 8. I'm increasing by a factor of 2 each and every single time. And so the number of nodes at that depth is going to be 2 to the K. Right? Verify. 2 to the 0 is equal to 1. 2 to the first is equal to 2. 2 to the second is going to be equal to 4. 2 to the third, right? 3 right here, 2 to the third is going to be 8. Right? Dot, 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 2 to the K. Now, what if I told you, dot, 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 that the depth of the tree is D? Then at that depth, there's going to be 2 to the D nodes. What I want to know now is what's the sum total? For that, we need to come up with a summation here. What I did is I ran K from 0 up to D. Right? So let me go ahead and put that over here. K is going to run from 0 up to D. And then I computed 2 to the K, right? It was 2 to the 0, 2 to the first, 2 to the second, third, dot, 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 K, and then finally the last one is going to be 2 to the D, okay? Does anybody have a closed form solution of this? Remember that this is going to end up being 1 plus 2 plus 4 plus 8 plus 16 plus dot, 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 2 to the D. Be careful, it is not Gauss's formula. Instead, this is now a series. Right? This is well, the other one was a series too, but this is a series of geometric series is what the term I'm looking for, right? Because it's geometrically increasing. It's increasing exponentially. So you tell me, what is the closed form solution of this? Do you know? No? Okay. It's going to end up being, there's a general form solution of this. The summation of K equals 0 up to D of x to the K is going to be something like x minus 1 in the bottom, and then x to the D plus 1 minus 1 or something like that, right? Look that up later if you're interested. I don't care. We're just looking at this for base 2. This is going to be 2 to the D plus 1 minus 1. Right? Let's verify that really quick. What if I had cut off the depth right here? Right? What is the sum total now? What is the subtotal right here? This is 1 plus 2 plus 4 plus 8. I get 15 out of this. That is equal to 2 to the third plus 1 minus 1, which is equal to 2 to the fourth, 16 minus 1, giving me 15. Verified. Right? If you wanted to actually prove this, by the way, you could use induction, say, from 235. Right? It's a nice little inductive exercise. So now why did I go through that exercise? Right? What if we could do the following? Right? If we can develop a way to insert, retrieve, and update or delete elements from a binary tree such that all operations are proportional, such that, let me separate that. One, all operations are proportional to the depth, and that's a big and, right? And we can guarantee that the depth is small, then we've achieved our goal. What do I mean by small? Let's come back over here. Right? Remember, what was I counting? I was counting n. Right? N is equal to the number of nodes. N is equal to 2 to the D plus 1 minus 1. I want to get a hold of D here because that's the depth of the tree. D is equal to the depth of the tree, T. Right? So help me out and solve for N. Well, let's bring 1 to the other side is equal to 2 to the D plus 1. How do I solve for D there? Take a logarithm, right, of both sides. Log of n minus 1 is equal to D plus 1. Right? Minus 1 on both sides, and I get finally that D is going to be log of n. Oh, sorry, that should be plus 1, right? Plus 1, plus 1, plus 1, minus 1. Right? In other words, go back to the big O analysis. D is going to end up being order what? Again, forget about this minus 1, forget about this plus 1. I end up with order log n. Gee, that sounds really familiar. Binary search? Binary search is exponentially fast. If I can achieve this, right, then I can get all three of those operations, insert, retrieve, and delete, right, and also up by implication update, right? Then I've achieved my goal, right? A full binary tree, right, a full or nearly full binary tree has a guarantee on its depth, right? It's going to be order log n, where n, let me go at D is equal to, right? Where n is the number of nodes, right? So by conclusion, if you can perform operations proportional to the depth, then operations will be efficient. Right. They're all going to be order, log n. Awesome. We've achieved our goal if we can do that. Right? I can insert stuff, I can delete stuff, I can retrieve stuff, and it's all going to be order log n if I can get these things, and that's a big if. We're not going to get fully there, but by the end of the semester, but we'll get really, really close. Right? Remember, the whole reason that we wanted to do this stuff is we want a data structure that supports all of these things, but is efficient with all of them. Linked lists were efficient in some cases, but inefficient in other cases. Array-based lists were just the opposite. They were efficient where linked lists were not, but then they were inefficient where linked lists were. Stacks and queues offered efficiency regardless, but that's because they were restricted access data structures. We now have a potential to exploit this data structure. Right? However, we need some implementations first. Right? So, before we get there, let's talk about how you would actually implement this in Java. Okay? What does a binary tree look like? Right? Binary tree has nodes. That node has data, whatever's stored in there. It also has a reference to the parent, to the child, the left child, and the right child. Right? So let's come over here to Java and start designing that. Okay? My first step is going to be able to create a class called a tree node. And immediately I'm going to parameterize it because I learned the lesson from all my demonstrations from the list-based data structure that it's better to start out with a parameterization here. Because it's going to hold data, right, of type T, private T element, right? It's going to hold that data just like a linked list did, just like an array-based list did, all right? But I don't want it to be just strings. I don't want it to just be integers. I don't want it to just be something. I want it to be whatever you want it to be, okay? All right, there's the tree node. The tree node has not just a next like a linked list, right? This looks kind of like a linked list if I were to orient it this way, right? A goes to the next, to the next, to the next, but it also has a right child. We need two of those things. And if you're wanting to traverse back up to the parent here, then you also need a reference to the parent. So private tree node of the same type of element, parent, left child and right child, left child and right child. There. That's a good start. In fact, I'd come back and I would have a constructor, getters, setters, maybe some additional convenience function like has left child, has right child, has parent, is root, stuff like that. In fact, let's do some of those. Public tree node, T element. What I'll do is I'll say you can create a tree node and put an element in it, but maybe you don't know who the parent is, maybe you don't know who the left child is, you don't know who the right child is until later on, right? So I'll go ahead and say, I don't know, this dot element is equal to element, right? There we go. And what about parent, left child, and right child? Parent, this dot parent is equal to null, right? That's a good placeholder to say, I don't have a parent yet, right? You haven't set the parent node of me yet, right? Left child and right child, similar. Left child is null, right child is null. I probably also want getters, maybe setters for each one of these. So let's go ahead and generate those. Right? In fact, let's go ahead and select all the getters, select all the setters, and go ahead and generate them. Right? Set left child, set parent, set, that all looks good, but maybe you don't want that. Maybe you don't want to set the element. Because once you put that element in there, I don't want you to ever change it. If you need to take this node and move it over here, trim the tree, and then graft it on over here, that's okay. But I don't want you ever changing that element. In fact, I could say that that's final. I'm never going to allow you to do that. All right, that's setters. Oh, I don't have getters. Let's go ahead and add the getters. I don't know why it didn't do that. All right. Let's go ahead and select the getters and generate those. Wonderful. Get element, get parent, get left child, get right child. You could also have some, say, Boolean functions has left child. Right? Remember we did this with a linked list. Do you have the next? Do you have a next? Right? And so here I'll return this dot left child is not equal to null. That expression, if it's not equal to the null, then you have a left child. Right? If it is equal to null, then you do not have a left child. That's going to be the same for the right child. Public Boolean has right child. Right? Return this dot right child is equal to null, or not equal to null, excuse me. Right. Maybe you want to determine how many children you have. Public int get num children. Children. Right. Well, how many children do you have? Right. If so, int value is equal to 0. All right. If this dot has left child, then I'll say value plus plus. Right? You have a left. You start out thinking that you have no children. If this dot has a left child, then of course, then you'll go ahead and increment that. And then if you have a right child, you'll also increment that. No, they don't. So the question was, can you treat a Boolean like an integer? You're thinking C, and no, you can't. And even in C, that's dangerous because 2 is also true, right? So be careful with that. Right? Okay, so 0, 1, or the other, or 2. Okay. What else might be convenient? Right? Boolean is root. How can you tell whether or not you're the root node? Well, here's the root node here. What's its does it matter that it has a left child? Does it matter that it has a right child? No. What matters is that it has no parent. Right? All right, so return this dot parent is equal to null. Right. Note here that I'm using equals equals instead of not equals because if the parent is null, then I am the root. If this is true, then this should be true. What's the opposite? Public Boolean is leaf. Right. What's an easy way of doing that? A leaf has how many children? 0. So return this dot get num children. Num children is equal to 0. Right. Just an application of all of the definitions that we just defined. All right. Maybe there are more convenience functions, right? Maybe there are other things that we can do with this. But this is one node, right? What would a binary tree look like? So let's go ahead and create a class called binary tree. And it's also going to be parameterized because we want it to hold whatever you want it to hold. Should I be keeping track of every single node? Private list of tree node of type T. There we go. All the nodes. should I be keeping track of all of them in a list somehow? That doesn't sound right. Instead, I'm going to keep track of one of them. And if I'm only going to keep track of one of them, which one should I keep track of? Some random one right in the middle? Some leaf node? I'm going to keep track of the root. Now, why am I keeping track of only one node? Because from that node, that tree node, T, root, from that node, you can get to any other node. All you have to do is traverse the tree. Remember, one of our observations is that from any node, you can get to any other node with exactly one path. It's visually, it's easiest to think of this as the root node, and from there, if you wanted to get to H, okay, just go ahead and traverse down over here. If you wanted to get to J, okay, just traverse down over here. From this node, you can get to any other node. The big question is how, right? So, I want to explore. I want to actually search in this tree, okay? I want to determine, get the data at node, say, J. All right, well, if all I'm doing is keeping track of this node A, do I know that it's over here where I can see it because I'm a human, I'm looking at the entire thing? That would be like keeping track of every single node all at once, right? But I can't do that, right? I'm only looking at local information here. Right now, as it stands, I am right there. Right? I'm basically standing right there and I can only see this node right here. All right, I've got two choices. I've got a maze now. I could go that way or I could go that way. If I went that way and I explored this entire subtree, I would find that, oh, I didn't find J. How do I know that I need to come back to this node over here and traverse down here to eventually find it over here? I need to keep track of it. So do you know how to solve any maze? Right? Of course, if it's the nice novelty maze at a restaurant, right? You just go, oh, dead end, right? Backtrack, oh, dead end. Now I've finally gotten out, right? But what if you were to do it in real life, right? And you're blind, or there's no light at all in the maze. Do you know the left-hand trick? Or the right hand, left hand, it doesn't matter, right? All you have to do is take one or the other hand, stick it on the wall. Just keep walking, right? As long as there's not like deadly pits or enemies or something like that. Just keep walking. You will eventually traverse around the entire maze until you get to the end of the opening or the exit or something, right? In other words, you don't have to look at the entire tree. You can be blind and you can still solve this. What would it look like to do this as a maze? I would start at the root node and go down over here. Right? I would keep I'll use my left hand then. I'm walking around the perimeter of this thing. So this is me, right? And here's my left hand going against this wall right here. Think of this as a wall. Then I'll traverse down over here, over here, over here. And you know what? I got to a dead end. So what do? I start turning around and I come back up over here. Oh, there's another corridor down over to my left side. Go down, go down. I reached another dead end. Come up, and you start to see a pattern here. What I'm doing is I'm traversing around the perimeter of this tree. There we go. There we go, and all the way up. At some point, I would have found the one that I'm looking for, right? When my left hand hits this one right here, then I can stop and say, I found that element. There you go. Right? So how do I go about doing this? There are lots of ways that you can do this, but there are three primary ways that we're going to look at it. Right? There's a pre-order traversal, an in-order traversal, and a post-order traversal. These are all actually the same traversal of walking around the perimeter of this tree, but you explore it in a different order. A pre-order traversal, if we've got, say, a node U, and then a left child and a right child. In fact, let me, I'll leave it like that. Actually, no, let's go ahead and do it proper. Let's go ahead and call it root node, a left node, and a right node. Right. So the pre-order traversal here is going to enumerate those nodes. In other words, list them out in a route. Then we're going to go to the left, and then we're going to go to the right. It goes in that order. So I'm going to look at this one and say, is that the one I'm looking for? No? Okay, then go down to the left and then explore that entire tree. I didn't find what I'm looking for. Okay, go down to the right and explore that entire tree. An in-order traversal is going to go down to the left first. In other words, before you look at this node, I'm not even going to look at it. I'm going to go down to the left and see what I can find there. When I come back up, I will then look and see what's stored in that node before I traverse down to the right. So left, root, and then right. A post-order traversal is going to be going a left, right, and then a root. In other words, it's going to go explore this entire left subtree first, entire right subtree second, and then finally, only after you're done with all of that stuff, do you look at the root node here. So you might be asking yourself, I've got 3 things. There are 6 permutations, right? You could have gone to the right before you went to the left, right? But then that's the same tree. Right? All you have to do is rethink of this tree as, I didn't get the R, but let me go ahead and rearrange the, can I arrange? No? Resize? No, I'm not going to be able to do that. All right, so let me go undo that. I can't do something what I'm going to try to do here, right? Just go root, and what I'm going to do is I'm going to take that right node, and I'm going to shove it over here. And then I'm going to take that left node, and I'm going to shove it over here. In other words, I'm going to look at the mirror image of it, right? And that's the same exact tree, same exact structure, but now you're going to the right node instead of the left node first. So we generally don't consider that. It's going to end up being the same pre-order, in-order, and post-order traversals as before. It's just that you're going to be doing the mirror image of it. So we'll discuss how to do this in detail next time.